Yes, we are live now. Please start.
Okay. Hello, everyone. My name is Diksha Bansal, and I am a teaching assistant in this course, Calculus of Variation. And today we are going to talk about the content of first
Yes,
three
we are
weeks.
live now. Please start.
Okay. Hello, everyone. My name is Diksha Bansal, and I am a teaching assistant in this course, Calculus of Variation. And today we are going to talk about the content of first
Yes,
three
we are live now. Please start.
Okay. Hello, everyone. Yeah, okay. So we will talk about the content of first 3 weeks today, and I'll be taking any doubts or queries regarding to these week's problems or any theoretical problems. So let us first discuss about what the topics were covered in these 3 weeks. In week 1, the instructor talked about give a brief introduction about the calculus of variation, what is COV, and what's the history behind this subject, how this subject evolved in during the 1880s or 90s timing, and what are the applications of this particular course. For example, some of the applications of calculus of variation involved in mechanics, in quantum mechanics, and in electrodynamics, and other applications which are very important in the area of economics, for example, in urban planning and in optimal control theory. Also in the, it's widely applicable in mathematics, where case study in geometry and differential equations are very done using the help of calculus of variations. So calculus of variation generally talk about few problems, very specific and famous problems, and it tries to analyze and solve those problems, those famous problems. And one of the those famous problem is the gold digger problem, in which we consider a field containing a particle of golds, and the objective is to collect the maximum amount of gold by choosing the best path. So the path length is generally limited, and the gold collected on the path is the integral of the gold at each point. So uh, uh, the objective is to collect the maximum amount of gold. So that is the problem that we try to tackle with the help of calculus of variation and by functional method. The next problem that he talked about is the catenary problem, which is a problem in the case if we consider a very thin, uniformly heavy, flexible cable, which is suspended from the top of two poles of different heights, and which is at a specific distance d, then what will be the optimal shape of the cable between the poles? So that is the catenary problem. And this cables assumes the cable that is connecting those different poles. This basically assume a specific shape which makes the potential energy minimum. So to minimize the potential energy, we use the calculus of variation method or the functional method and find out a formula which is helpful in finding that optimal shape of the cable between these two poles. Okay. Then he introduced catenoids. And what are the catenoids? It is the generalization of catenary problems. And it's the surface of revolution with minimum area that is generated by revolving the catenary. Okay. So we try to create a new functional, a new extremal for this functional, and then we try to solve it. Then after that, he talked about the famous brachistochrone problem, in which we try to find the shape of a wire along which a bead is initially at rest, slides from one end to the other as quickly as possible under the influence of gravity. Okay, so basically in this problem, we use some assumptions. That is one of the assumption is that the endpoints are fixed. Both the endpoints through which a wire is hanging, those endpoints are fixed. Second, the motion is assumed to be frictionless. There is no friction assumed as this problem. And the third assumption that we take is continuous and, or we can say piecewise differentiability that we assume in this problem. So we try to find a solution to this problem by optimizing the functional that we obtain for brachistochrone problem. Then next, he talked about the DDoS problem, DDoS isoparametric problem, which says that what is the shape of the curve which encompasses the largest area given fixed length of the curve. Okay. So we try to find the shape of the curve. So you can say all the problems are generally used to explain the shape or the behavior of the wire or the curve of specific or famous problems. Okay. Then he talk about differential geometry problem, that is the geodesic problem, and in which we need to find the optimal curve with the minimal arc length. We have some surface and we have points P0 and P1, that those points are lying on the surface, and we try to find the optimal curve. So the calculus of variation is all about finding the optimal solution, the optimal curve or the optimal behavior of the solution. So we try to find the optimal curve of the surface with minimal arc length. That is what the geodesic problem says. Then he talked about minimal surface area and the optimal harvest strategy problem, which is very popular problem in economics, and it's very useful there. So it's basically says how to find a harvesting strategy that maximizes profit. So then that is the problem of the optimal harvesting strategy. Okay. So then he did some revisions, some basic revisions of extremals in finite dimensional calculus, where he talked about the functions of one or several variables. And then he talked about the famous and basic Euler-Lagrange equation. Those are the basic revision concepts that he introduced, so that we can easily capture the essence of the topic that we are going to study in the next few weeks. Okay. Then that was the content of week 1. In week 2, he talked about special cases of Euler-Lagrange equation. And those special cases, he discussed 3 to 4 special cases for Euler-Lagrange equation. The first case was the functions depending on y. The second case was the functions with no explicit x dependence. That means the x dependence was not explicitly involved in the function. It was implicitly involved somewhere. Otherwise, it's completely independent of x. First one was the functions depending on y prime only, y derivative only. And the third case, he talked about the functions with no explicit y dependence. That means the function were not depending on y explicitly. And the fourth, he talked about degenerate cases. Those were the 4 cases that he talked about in the special cases of Euler-Lagrange equation. And we got to study how to find the solution for these particular 4 cases. Okay. Then he talked about invariance of Euler-Lagrange equation. In these 4 cases, we find the form that is coming after introducing these restrictions, that is the function depending on y prime or y. So we got different kind of Euler-Lagrange equation solutions for different type. Okay. Then he talked about the invariance of Euler-Lagrange equation. How is it and under what circumstances it is invariant, and what is the condition for existence and uniqueness of the solution. What are the reasons for the existence, reasons to happen to get the unique solution and the existence of the solution. How is the solution going to exist? Okay. Then he talked about some generalizations. That is, the first one was involved in functionals containing higher derivatives. That means if we have derivatives higher than first derivative, then y apart from y prime, the standard definition involves f as a function of x, y, and y prime. But the special functionals which is the generalization case of the normal functional case scenario, in which we have the functions depending on x, y, y prime, and y double prime, y triple prime, or any up to higher order, any higher order till now. Then he talked about generalization. The second point, he talked about generalization containing several dependent variables. In the standard scenario, we had only one independent variable, that was x. X is the dependent variable, y is the independent variable, and y prime is the derivative of that independent variable with dependent variable with respect to the independent variable. But we can possibly have functionals which contain several dependent variables, say x1, x2 up to xn. These are different n independent variables, and then we have dependent variable y and the derivative of y with respect to all the xi's. And he talk about those general cases and find the equation for functional equation for these general cases. Okay. After that, he talked about functionals containing, the third case was the functional containing two independent variable. That means we have one dependent variable x, but we have independent variable y1 and y2. And we have, of course, derivative with respect to those independent variables y1 prime and y2 prime. So that is also a possibility. And in that case as well, we will have a different kind of equation which will describe the functional form of those equations. Okay. After that, in week 3, in the end of week 3, he talked about some numerical solutions and the methods, how can we numerically solve the problem. And in that scenario, the first one was the Euler's finite difference method, in which he talked about how can we numerically solve with the help of this finite difference method, how can we numerically find the solution of it. Then he talked about ridge method. In the second case, he talked about ridge method and how can we find a numerical solution using ridge method. If we don't have if we have the exact solution, we can definitely check, and because for ridge method we can have multiple solutions, but the most effective solution is the one which is closest to the exact solution which we find by Euler's equation. So the ridge method gives us a specific and a perfect way to find the closest possible solution for the problem, and it generally gives an upper bound to our solution as the method suggests. It approximates our variable using family of linearly independent functions, and it reduces the problem, the complicated problem, into standard multivariate minimization problem for unknown CIs. So in that way, ridge method try to solve the problem by choosing a function phi I such that it satisfies the boundary condition as well. Okay. And then in the end, the third method, he talked about.
Hello.
Hello.
Yeah, excuse me. Are you sharing your screen?
No, I'm not
Okay,
sharing.
okay, fine. Somebody's asking, so yeah, fine.
Okay. Yeah, okay. And the next third method that he talked about is the Kendrobits method. This is the method for more than one independent variable, in which case we try to approximate our function z with the help of some function phi and the basis function phi i's. And we chose phi I such that it satisfies the boundary condition, satisfies the homogeneous condition, and phi naught satisfies the boundary conditions. Okay. Then this is the content for the end of third week. In the fourth week, I'll give you a brief introduction about the fourth week because it only got live 2 or 3 days back. So in the week 4, he talked about the isoparametric problem, in which he talked about the finite dimensional case and the Lagrange multipliers, including single constraint, multiple constraint, and abnormal problem. So I give a brief hint about the isoparametric problem before at the starting. So he talked about this problem and different cases which involves different constraints, like single constraint, multiple constraint, or abnormal problem. So he talked about those cases and introduced the concept of Lagrange multipliers. Then he talked about the isoparametric problem involving functionals, including cases of generalization in higher dimension. And then also he talked about multiple isoparametric constraints and several dependent variables. So we can discuss about this 4 weeks content in the next meeting as well, in the next live session as well. So this is basically the content of the 4 weeks that the instructor has introduced, and that's it. Okay. So if you guys have any problem or anything to discuss, you can post it on the YouTube channel, or you can comment it on the Zoom link as well.
Yes, I think we can close now.
There are no doubts.
Yeah, no doubts were there.
Okay. Okay. Thank you, everyone.